Right, so lecture 26 already. And I want to go over the second exam. And it starts as follows. So question 1, we have a linear operator T from our ordinary Euclidean space R3 to itself, defined by T of the vector x, y, z is the vector 4x plus y minus 3z minus y x plus 4z. And if we take the standard basis, E1, E2, E3, the matrix for T with respect to this basis is what? Well, T of the vector E1, that's T of the vector 1, 0, 0. When x is 1 and y and z are 0, you get 4, 0, 1. That's the first column of the matrix. T of E2, which is T of 0, 1, 0. So when y is 1 and x and z are 0, you get 1 minus 1, 0. So that's the second column of the matrix. And T of E3, which is T of the vector 0, 0, 1, when z is 1 and the other coordinates are 0, you get minus 3, 0, 4. So that's the third column of the matrix. So that's the matrix of T with respect to the vectors in the standard basis. That's part A. Any questions about this?
Professor, I thought on the test it was 7z for the third.
Oh, I'm sorry. I just wrote it down wrong. So this would be minus 307. Thank you. That just makes this a 7. Okay. Part B, we consider the subspace W of all vectors whose second coordinate is 0. So all vectors x, 0, z, where x and z are in R. And we want to show that W is a T invariant subspace. Let's see, well, what's an easy way to do this? If I take T of a vector x, 0, z, so that's, well, I can use this or the matrix, but when y is 0 and x and z or whatever they might be, this is 4x minus 3z, 0, x plus 7z. And this is certainly in W because the middle coordinate, the second coordinate is 0. So T of W is in the space W for all vectors W in the subspace W. That means T invariant. That's what this shows. And if we take another subspace, maybe I should have called them, given them different letters, doesn't really matter. Let's say W2 is the subspace of all vectors whose only non-zero, whose first and third coordinates are 0. The second coordinate can be anything. What is T applied to a vector 0, y, 0? When x and z are 0, oops. Oh, good. So when x and z are 0, I get y minus y0. This is not in W2 if y is different from 0. So that means this W2 is not T invariant. Because it's not the case that the linear operator T maps every vector in W2 to a vector in W2. So for example, if you took 0, 1, 0, that would get mapped to 1, minus 1, 0. First coordinate's non-zero. So that's part C. So any questions about that? All right. So that was problem 1 on the midterm. Let's look at problem 2.
If we just put, sorry, 1 second. I just wanted to look at my answers real quick. If we put like, if we made like, the T and the W just equal to each other and put for every like W, it's a subspace because they have matching numbers or whatever, it's fine, right? Even if we didn't write it. Sorry.
You mean for part B?
Yeah, for part B. As long as we like equated them together, would it still have been fine?
So I have to look at the paper and see, because what you're saying in words doesn't tell me what you wrote down. But when I look at your exam, I'll let you know.
All right, thank you.
All right. Or if you really, or maybe what you should do is after class, just send me an email to remind me, to let you know by some message, email or whatever, how I understood what you did on this part of the problem, and I'll write back to you right away.
All right, thank you.
Sure. All right. Problem 2. So in problem 2, we're trying to find the spectrum of a matrix. So we have a 2 by 2 matrix, 4, 2, minus 1, 1. And the spectrum of A is the eigenvalues of A. And lambda is an eigenvalue of the matrix A if there exists a non-zero vector. So we're in 2 dimensions. I can write my vector as x, y, a non-zero vector such that A of x, y is the scalar multiple lambda of x, y. So we have to find the eigenvalues in part A, and in part B, we have to find an eigenvector, such a vector xy non-zero that satisfies this equation. So let's just write out what this means, what this is. The matrix is 4, 2, minus 1, 1 times xy. When you do your matrix multiplication, this is 4x minus y and 2x plus y. And we want that to be lambda of x times xy, which is lambda x lambda y. So the number lambda and the vector xy satisfy this equation if 4x minus y equals lambda x and 2x plus y equals lambda y. Or so this is basically high school algebra, 2 equations and 2 unknowns. So this is the same as if I put everything over on, let's say, on the right side of the equation. Lambda minus 4 times x plus y equals 0. That's the first equation. And minus 2x plus lambda minus 1 times y equals 0. That's the second equation. I bring this over here, I get minus 2x plus lambda y minus y. That's lambda minus 1y equals 0. Lambda minus 4 times x plus y equals 0. And so we want to know for what lambda, real numbers, does this system of two linear equations in two unknowns, two variables, x and y, have a non-zero solution. That means a solution where x and y are not both 0. And that happens if and only if this determinant of these equations is non-zero. So the determinant, right? I mean, if you have ax plus by equals 0, cx plus dy equals 0, this has a solution where xy is not 0, 0, if and only if the determinant ad minus bc is 0. And so that's this little bit of linear algebra, which is basically high school. So this is A, this is B, this is C, this is D. So we want to know when is lambda minus 4 times lambda minus 1 minus 1 times minus 2 equal to 0. That's lambda squared minus 5 lambda plus 4 plus 2 equals 0. Or lambda squared minus 5 lambda plus 6 equals 0. Well, this is a simple quadratic equation. Actually, the left side factors, this is lambda minus 2, lambda minus 3 equals 0. So lambda is 2 or 3. So from this analysis, we get that the only possible eigenvalues are 2 and 3. And in fact, for both 2 and 3, the set of equations has a non-zero solution. So this tells us that the spectrum of the matrix A has 2 eigenvalues, 2 and 3. And how do we find eigenvectors? Well, so we want to find x and y such that
Excuse me, Professor. For the spectrum, right? Does it matter like if 3 is like before 2, as long as you have those 2 numbers in the spectrum, right? Or
well, it's a set. So there are 2 eigenvectors, 2 and 3. So the set of, I mean, these, it's not an ordered pair.
okay.
So, right, it's just.
I just wanted to make sure.
3, 2, 2, right? This is not a set with 5 elements. This was just a set with 2 elements, 2 and 3, and I just sort of foolishly wrote down 3 times and 2 twice, but they're all the same set. The only element, the elements in each of these sets are 2 and 3, so it makes no difference. Right? It's not an ordered arrangement of eigenvalues. It's just a set of eigenvalues.
Great. Thank you, Professor.
So we're trying to solve, for example, if we take the eigenvalue 2, we want to find a of xy equals 2xy. Find a vector that satisfies this vector equation. And so again, a of xy, that's the matrix 4, 2, minus 1, 1 of xy. That's 4x minus y, 2x plus y. And we want that to be equal to 2x, 2y, which means we want 4x minus y equal to 2x, and 2x plus y equals to 2y. And each of these equations is the same as 2x minus y equals 0. 2x minus y equals 0, or y equals 2x. So xy is x and y is 2x. That's just x times the vector 1, 2. So the eigenvectors, the eigenvector, you can take the vector 1, 2, or any scalar multiple of it. But you just have to find one eigenvector. So 1, 2 is an eigenvector for the eigenvalue 2. So we found from looking at those equations that the eigenvalues are 2 and 3. So let's take lambda equal 2. We want to find an eigenvector. That means we want to find the non-zero vector xy such that a of xy is 2 times xy. When you write that down, that's simply this set of equations, or these equations, which are the same as just this one equation, which is the same as y equals 2x. So any vector where the second coordinate is twice the first coordinate is an eigenvector. That is any scalar multiple of 1, 2. Any questions about that? Suppose we take lambda equal 3. Then we know there's a non-zero vector xy such that a of xy is 3 times xy. But when you write that in equations, you get, it's exactly this, only now it's 4x minus y equals 3x, and 2x plus y equals 3y. And these equations are exactly equivalent to x minus y equals 0 or x equal y. So you can take the vector, for example, 1, 1. So the vector 1, 1 is an eigenvector for the eigenvalue 3. So we have this 2 by 2 matrix, and it turns out there are exactly 2 eigenvalues and 2 eigenvectors. And one reason why eigenvalues and eigenvectors are so important is if you look at the 2 eigenvectors, if I take the vector 1, 2 and the vector 1, 1, this is in fact a basis for R2. These vectors are linearly independent. And if we take a vector v and write it as some scalar multiple of 1, 2 and 1, 1, then if you want to understand t of v, so let's call this vector e1 and this vector e2. So I'm writing v as x times e1 and y times e2. So t of v is t of x e1 plus y e2. So t is just, let me write this as A is the matrix. So this is A x e1 plus A y e2. That's x A of e1 plus y A of e2. But these are eigenvalues. This is just 2e1 and this is 3e1. So this is 2x e1 plus 3y e2. So if I'm writing a vector with respect to a basis of eigenvectors, if x, y is the coordinates of the vector with respect to this new basis, A of this is just 2x, 3y. It's a very, very simple way to understand the action of a matrix. It just stretches each coordinate by a fixed amount, the amount of the eigenvalue. Yeah. So if you have a matrix or a linear operator and you can find the basis of eigenvectors, you have an extremely simple way to describe the action of the idea of the matrix on vectors. Anyway, that's problem number 2, which suggests that we are followed, it is followed by problem number 3. So in problem 3, we're in Euclidean space R3 with the standard inner product, and I have vectors v and w. And we just want to do some simple calculations. The inner product of v and w is it's the sum of the products of the coordinates. 2 times 5 plus minus 1 times 0 plus 2 times 3. So that's 10 plus 0 plus 6. So if my arithmetic is correct, the inner product is 16. The length of v squared is the inner product of the vector v with itself. So when you take the inner product of this with itself, it's 2 times 2 plus minus 1 times minus 1 plus 2 times 2. That's 4 plus 1 plus 4, that's 9. So that's the square of the length. So the length is the square root of the inner product of the vector with itself. That's the square root of 9. So this vector has length 3. And if we want a unit vector in the direction of v, it's 1 over the length of v times v. So that's 1/3 the vector v. That's 1/3 the vector 2 minus 1, 2. So that's 2/3 minus 1/3, 2/3. So this is a unit vector in the direction of v. Any questions of that? Nothing. Right. Simple vector analysis. Problem 4, we're back to R2 with the standard inner product, and v is the vector 2 minus 7, and w is the vector 5, 6. So if you wanted to sketch where these vectors, what these vectors look like when you graph them in the plane, so this is 2, 4, 6, minus 2, minus 4, minus 6, minus 8, 2, 4, 6. So 2 minus 7, that's down here somewhere. So this is v, which is 2 minus 7. And 5, 6. It looks like it's up there.
Were we supposed to label it with the coordinates or just labeling it as like v, w, v parallel would have been fine?
Well, when it says to draw the graph of the vectors, I don't know how you do it without coordinates. And how can you see what the vectors are?
The coordinates are like on the side. They're not on the actual.
Oh, you mean putting the coordinates right here?
Yeah. Instead of putting the coordinates
Oh, you
right
don't
there,
have to do
put it
that.
like to the side of the graph
Yeah,
instead.
no,
so
that's
they didn't
fine.
have a lot of.
If you have coordinates on your axes and you don't have to put this here. If that's what you're
Okay.
asking. I'm just trying to make everything as explicit as I can.
All right.
Okay. So we want the component of v parallel to w. So this is w. And if you look at the line, the one-dimensional subspace it generates, the component of v parallel to w would be, something like this. If we're just trying to see what it looks like roughly, this in red, this would be the component of v parallel to w. But that's just a picture. I need to actually compute it. That's the problem. So v parallel is, I take the inner product of v with w divided by the inner product of w with itself times the vector w. So this is a scalar multiple of w. So this is something on this line, this one-dimensional subspace through w. What are these numbers? The inner product of v and w is 2 times 5 plus minus 7 times 6 over the inner product of w with itself. That's 5 times 5 plus 6 times 6 times the vector w, which is 5, 6. So this is 10 minus 42, that's minus 32, and 36 and 25, 36 and 25, I think is 61. So this is the vector. So it's this vector multiplied by this number, which is a little bit more than a half. I mean, officially it is 5 times 32 is minus 160 over 61. And 6 times 61 is 366. Oops, that sounds not right. 5 times 30. Sorry. 6 times 32. 6 times 32 is 192 minus 192 over 61. So those are exactly the coordinates of V parallel. This is yeah, and just to see that this actually coincides with our rough drawing, 32 over 61 is approximately 3 over 6 or a half. So it's minus a half. So this would be a vector in the opposite direction of W and about half the length, which is what it looks like. In any case, this right here is exactly V parallel. These are the coordinates. And this vector, which I'll make in green from here to here, or as a vector which really looks like that, this is going to be V perp. And the perpendicular component of the vector V with respect to W is V minus V parallel. So that's 2 minus 7 minus this vector minus 160 over 61 minus 192 over 61. So if I wanted to actually write this down exactly, this is 2 minus 7 minus times minus plus. Let me just write this as, just to avoid fractions slightly. No, I don't have to do that. 160 over 61, 192 over 61. Let's see. 2 is the same as 2 times 61 over 61. So that's 122 over 61. 7 times 61 is 427 over 61. Plus 160 over 61, 192 over 61. So if I can add these properly, hope I can, I get 282 over 61, and 427 minus 192 is minus, see 7 take away 2 is 5, denominator is 61, 12 take away 9 is 3, 3 take away 1 is 2. So that's the vector that I get. I mean, roughly, just so we can sort of estimate, this is a roughly minus 4, and this is, see, 244. This is between 4 and 5. So I don't know, let's just say roughly 4.5, just to look in. And if you look at this, that's exactly what this looks like. I mean, these are exactly the coordinates of this vector. And if you take, this is V. If I take V parallel and V perp, these are perpendicular, and I add them together, this is exactly what I get. So that's problem 4. This is just simple vector arithmetic. If you've taken Calc 3 or freshman physics, you would have spent a lot of time just decompose. In physics, you take a force and you decompose it into parallel and perpendicular components of the force. That's what this is. Just simple vector stuff. Any questions about that? All right. Good. Graham-Schmidt, very important. So in problem number 5, we have a basis for R2, which are the vectors 3, -2, and 1, 5. And apply Graham-Schmidt, the Graham-Schmidt process, to get from these an orthonormal basis. Orthonormal basis. Well, first we get an orthogonal basis, and then we divide each of the vectors in that basis by their lengths to get unit vectors, and therefore an orthonormal basis. So let's say we let V1 be equal to 3 - 2, and V2 to be 1, 5. These are the vectors we start with. So the first vector in the new basis in this first step isn't going to change. W1 is just going to be the same as V1, which is 3 - 2. And W2 will be the component of V2 perpendicular or orthogonal, the same thing, to W1. So what is W2? It's the perpendicular component of V2 with respect to W1 or V1. So this is going to be equal to V2 minus the parallel component of V2 with respect to this vector. So that's the inner product of V2 and W1 divided by the length of W1, which is what my W2 is going to be times W1. So V2 is the vector 1, 5. The inner product of V1 and V2, or W1 and V2, are 3 times 1 plus 5 times -2 over the length of W1 squared, that's 3 squared plus -2 squared, it's that number, times the vector W1, 3 - 2. So that's the vector 1, 5 minus, this is 3 minus 10, it's -7, minus -7 is plus 7 over 3 squared and -2 squared is 9 plus 4 over 13 times 3 - 2. So this is equal to 1, 5 minus 7 over 13 times the vector 3 - 2. So it's a scalar multiple of this vector. 3 times 7 over 13 is 21 over 13. And the other coordinate is minus 14 over 13. So this is, if you put everything over common denominator of 13, this is 13 over 13, 65 over 13, minus 21 over 13 minus 14 over 13. So that's equal to minus 8 over 13, 65 plus 14. I'm doing my arithmetic correctly, there's no reason to think I am, is minus 8 over 13, 79 over 13. Let me double check everything because I always believe I make mistakes in arithmetic. So I have the vectors 3, -2, and 1, 5. I want to find the component of 1, 5 perpendicular to 3 - 2. So it's the vector B2, which is 1, 5, minus the component of this vector in this direction. So the inner product of these two vectors is 3 - 10, it's -7. minus 7. And the length of the vector v1 is squared is 13. 3 plus 9 is 13. So it's minus 7 over 13, which is plus 7 over 13 times the vector 3 minus 2. So that's 21 over 13 minus 14 over 13. And 1, 5 1/5 is the same as 13 over 13, 65 over 13. So in the unlikely event this is correct, you get minus 8 over 13, 79 over 13. So I would have my orthogonal basis, W1, would be equal to my original vector, 3 minus 2. W2 would be this vector, minus 8 over 13 and 79 over 13. And these vectors are supposed to be perpendicular, but they're definitely not. So I have to find out where I made my arithmetical error. 3 minus 2 and 1, 5. And parallel component. The component of V2 parallel to V1. We take the inner product, minus 7 over 13 times the vector 3 minus 2. It's 7 over 13 times this vector. It's 21 over 13 minus 14 over 13. And 1, 5 if I put this over the denominator of 13, this is 13 over 13 and 65 over 13. So and it's clear if I multiply, if I take the inner product of W1 and W2, I do not get 0. So what is that? I'm really puzzled. Let's see. If anyone can see where I did the arithmetic incorrectly, please let me know. I have the vector 3 minus 2 and the vector 1, 5. So the component of 1, 5 parallel to 3 minus 2 is a certain scalar multiple of 3 minus 2. And this is the scalar multiple. I take the inner product of these two vectors, which is definitely minus 7, and divide it by the length of this vector squared, which is 9 plus 4 is 13, times the vector 3 minus 2. So that's minus 21, 14, over 13 again, minus 21 over 14. And then I subtract so this is minus 21 over 14. And then when I subtract, Which maybe this is it, maybe this becomes a plus. So this is 34 over 13, and 65 minus 14 is 51. So minus 34 over 13 and 51 over 13. And let's just check. What is the inner product of W1 and W2? It's 3 times minus 34 over 13. Minus 2 times 51 over 13. I'm almost there, except I have a sign wrong somewhere. So this is minus 102 over 13. And this is also 102 over 13. So, oh, this is plus. This is plus. Okay, perfect. Oh, good. So 102 minus 102 is 0. So here's the orthogonal basis that we get from Graham-Schmidt. 3 minus 2 and 34 over 13 and 51 over 13. And then I'm not going to do the arithmetic. If you divide by the lengths to get unit vectors, these two vectors are the orthonormal vectors in the Graham that you get from the Graham-Schmidt process. So advanced mathematics is nice, but you have to do elementary mathematics correctly also. So, and the way I knew I was making a mistake over and over, making mistakes, was that my vectors W1 and W2 that I end up with have to be perpendicular. The inner product has to be 0. And now everything is nice and correct, and the inner product is 0. So all is well with the world. Okay. In fact, this vector is, I can factor out as 7 over 13. It's 7 over 13 times the vector 2, 3. And 3 minus 2 and 2, 3 are definitely perpendicular. So this is actually very nice to see. If you wanted to get the unit vectors, let's say E1, which is W1 divided by its length, the length is 13. This would be 1 over 13 times the vector 3 minus 2. E2 would be this vector divided by its length. Its length is also 13. Divided by its length, 1 over the square root of 13. And this vector, the length of this, would be 17 over 13. So the reciprocal 13 over 17 times 1 over the square root of 13 times the vector 2, 3. And these vectors have unit length. Actually, sorry, it's easier than that. Dividing by the length, the 17 over 13 cancels, and you get 1 over root 13. So these vectors have unit length, and they're perpendicular, and these are the two vectors you get from the Graham-Schmidt process. That's it. So these aren't actually so complicated in the end. They look rather nice. Okay, that was problem 5. Let's look at problem 6. So again, we're in R2 with the standard inner product, and in R2, suppose we let X be the set of just one vector, W, which is the vector 1, 1. And we let X perp be the set of all vectors xy in R2 such that v and w, this is w, are perpendicular. That means their inner product is 0. If you want a picture of this, of course, it's very easy to see. Here is the vector w, which is 1, 1. The subspace it generates is just this, the line x equal y in the plane. And perpendicular to it, this one-dimensional subspace will be x perp. But how do we actually calculate that? So xy, that vector is in x perp, if and only if, let's call this v equals 1, if and only if the inner product of v and w is 0. The inner product of v, which is xy, and w, which is 1, 1, is x times 1 plus y times 1 equals 0. That's just the line, x plus y equal 1, or y equals minus x. So it's all vectors where y is minus x. That's just all scalar multiples of 1 minus 1. Here's the vector 1 minus 1, and the scalar multiples of it are this line. So x perp is the one-dimensional subspace spanned by the vector 1 minus 1. And this is the picture of, here's my vector w, which is the only vector in the set X. And the subspace is this line through the origin going through the point 1 minus 1. So that's my x perp. Okay. Any questions about any of that or anything else that was on the exam?
I think you got it.
Thank you. Okay. Let's talk a little bit more about these, what you might call the geometry of vectors. In the plane or in 3 space or in any vector space. Again, the picture is always like this. So let's say here's some one-dimensional subspace. This is in your vector space. This is the origin, this is 0. And so this is some subspace W. And you have some vector V, and you think of decomposing V into a vector. Well, if this were a one-dimensional subspace, which is what it looks like the way I've drawn it, this is the component of V parallel to W. I have this vector here. Let me, what should I call this? I was calling this V parallel if this was one-dimensional, or another way of talking about this is the component, COMP stands for component, of V with respect to W. That's this. And if you look at all possible vectors on this line, like here's another vector on the line, and here's another vector on the line. This component has the property that it's the vector in W where the distance to V is as small as possible. This is shorter than this line or any other line. And you can think of this in more than one dimension. So suppose you're in 3 space And here's a two-dimensional subspace. And you have some vector v, which is not in the subspace. And you would like to do something analogous to dropping a perpendicular from v into w. And then this vector v consists of this vector in w, which is the component of v with respect to the subspace w. And this vector in w will have the property that it's also the vector in w, which is the closest possible vector to v. So if I were to take any other vector in w, the distance to v would be bigger. This is the shortest distance. So there's a theorem that underlies what I'm saying in this sort of informal way. The theorem says that if V is an inner product space, like Rn, space with an inner product, and W is a finite dimensional subspace for every vector V in the whole vector space, there is a unique vector. So this is an example of an existence and uniqueness theorem. There exists a unique vector W0 in W, which is the closest vector to V, such that the distance from V to W0 is strictly smaller than the distance, the length of the vector from V to W, for all W in W. So if this is the vector V, this is the 0, this is W0, it's the vector in the subspace W, which is the closest vector to V. And there is such a vector, and it is unique. And the simplest way to prove this is to pick an orthonormal basis for W. So let dimension of W, let's say it's equal to K, and using the Gram-Schmidt process, for example, you can always find an orthonormal basis so that E1, E2 up to E sub K be an orthonormal basis for W. So that means that, first of all, this is a basis for W. The inner product of any two vectors in this basis, this is equal to 0 if I is different from J. So if every two different vectors in this basis are perpendicular to each other, their inner product is 0. And if you take the inner product of a vector with itself, you get 1. So the square of the length is 1, and the only number, positive number of the square is 1 So the inner product of EI and EJ is 0 for I different from J and 1 if I equals J, which is exactly what we call this function delta IJ. This is the so-called Kronecker delta. The Kronecker delta is defined to be, it has two variables, I and J. If I equals J, it's 1. If I is different from J, it's 0. And when you have an orthonormal basis, the inner product, EI, EJ, is exactly the Kronecker delta. That's an equivalent definition for orthonormality. So let V be any vector in the vector space, and we define a vector W0 in the subspace W as follows. W0 is going to be some linear combination, going from 1 to k, of this vectors that are a basis for W. And the coefficients are going to be the inner product of V with EI. And you might just check that VEI, inner product with EI, is the component, just the definition, the component of V parallel to EI. We would normally write this as this inner product divided by the inner product of EI with itself, but that denominator is just 1. So I'm letting W0 be, I take my vector V, and I'm taking the component of V in the x direction. This is in 3 dimensions, the way I've drawn it. The component of V in the y direction, and I'm adding them up. So this is my W0. I haven't drawn it so well, but. So I'm saying for any vector V in the vector space, define W0 to be equal to this. And this is certainly in W. If I take V minus this vector W0, and I take the inner product with EJ for any vector EJ in this basis, what is this? So V minus W0 this is VEJ minus W0 EJ. It's by the bilinearity of the inner product. This is VEJ minus, and W0 is this. W0 is summation. I goes from 1 up to k. Inner product of V with EI times the vector EI. That inner product with EJ. By the bilinearity, this is VEJ minus summation. I goes from 1 up to k, VEI, inner product EI, EJ. But this is delta IJ. This is 0 unless I is equal to J. And when I equals J, you get VEJ minus VEJ, which is 0. So I have my vector V. I have this W0, which is a vector in the subspace W0. This vector is V minus W0, and it's perpendicular to this plane. It's orthogonal to every vector in W. Now, I want to prove that the distance from V to W is strictly less than the distance from V to W0 for all W in the subspace W, except for W0. That is, that this vector W0 of all the vectors in the subspace W is the one closest to V. So I can write W as some linear combination of the basis vectors, xj, ej. J goes from 1 up to k. And so here's W. And if I take V minus W0 inner product with W. What is that? That's V minus W0 inner product with summation xj ej. K goes from 1 up to k because this is the vector W. By expanding, again, using the bilinearity of the inner product, this is summation j goes from 1 up to k, V minus W0 inner product with ej. But I just proved all of these is equal to 0, are equal to 0. So this is 0. So V minus W0 is perpendicular to W. If W is in the subspace W, and W is not the same as W0, then W minus W0 is not the 0 vector, right? If these two vectors are different, the difference can't be 0. But V minus W0 and W minus W0 are perpendicular. Because the inner product of V minus W0 is 0 with every vector in W. And we proved the Pythagorean theorem in an inner product space. Which says that if you have A, B, and C vectors, and A and B are perpendicular, the length of A squared plus the length of B squared is the length of C squared. Where C is equal to A plus B. C is A plus B. So V minus W, the length of this vector squared, this is the same as V minus W0 minus W minus W0 squared. Or maybe I should write V minus W0 plus W0 minus W squared. That's equal to the length of V minus W squared plus the length of W0 minus W squared. And this is positive, because this is a non-zero vector. Vector is length 0 if and only if it's 0. So this is greater than V minus W squared. And this is what I wanted to prove, that if I take any vector in the subspace W, different from W0, the distance from V to W is strictly bigger than the distance from V to W0. So this component of a vector V with respect to a subspace W is the vector in the subspace that is the absolute closest to your vector. And this has a lot of useful applications in many different fields. Statistics, economics, many things. People. So let's see, maybe I can give one example of how this is useful. So remember, the origin of linear algebra is the problem of solving a system of linear equations. In high school, you start with 2 equations and 2 unknowns. And In linear algebra, you end up with m equations and n unknowns. So m equations in n variables. And the typical problem is find all solutions. But sometimes you have equations that have no solutions. Suppose here you have two equations in one variable, x equal 1, x equal 2. There's no solution to this system of equations. No solution. Because x can't be equal to 1 and 2 simultaneously. But in a case when you have a system of equations that has no solution, you might ask for the best approximate solution. So what that would mean is the following. Here we have a system of equations, a11x1 plus a1n xn equals b1, am1x1 up to amn xn equals b sub m. Suppose there's just no solution. There's no set of n numbers that satisfies all m of these equations simultaneously. But what you could do is the following. Choose somehow or other x1 up to xn. And suppose a1, x1, and so forth up to a1, xn, a11, a1n, am1, x1, plus a, m, n, xn. This is some number I'll call b1 hat, and so forth, b, m hat. These are the numbers you get. And this set of numbers, b1, this is like an m-dimensional vector. It's not a solution because there is no solution. But we might want to say, can we choose x1 up to xn such that, let me call this the vector b and this the vector b hat, such that the length of b minus b hat, or the length squared, it's the same thing, is as small as possible. So even though you cannot solve this set of equations exactly, we could ask for the set of solutions where if you compare these numbers with these numbers, and a simple way to do that is to take the sum of the squares of the differences of the coordinates. So that's what we want to see, if we can minimize the summation I goes from 1 up to n, bi minus bi hat squared. That's what the length of this vector squared is. We like to minimize this. And a vector that minimizes this is called the best least squares solution to the problem of solving these linear equations. It gives you the smallest least squared error. And it turns out that the following is true. So in my notes, I wrote this as a theorem. I don't think I'm going to prove this, and maybe this is just for the point of view of general education about linear algebra. It's an interesting topic. But we had another couple of weeks, I would spend a big chunk of the time on this. So we have m equations in n variables. Right? Looks like a1, 1x1 up to a1 n xn equals b1 down to the mth equation am1x1 plus amn xn equals b sub m. In matrix form, you would write this, you would have the matrix A, which is the matrix of coordinates, a1, 1 up to a1n, am1 up to amn, and you would have the vector x, which is x1 up to xn, and the vector b, which is b1 to b sub m. And you can write this equation equivalently in vector form. This is ax equals b. You take ax equals b and you equate coordinates, you get exactly this system of equations. And we want to find the least square solutions. So this is an m by n matrix. X is in Rn, B is in Rm. And the least square solutions, there's a way to write, I guess this doesn't really, it's hard to understand without the proof. You look at all vectors in Rn such that Ax is, you take the component. So here we have our matrix. We have these different column vectors. So W is the column space of A. So this is the space, the subspace of Rm generated by the n column vectors. That gives you a subspace of Rm. And we look at all vectors in Rx such that Ax is the component, take the component of the vector B with respect to the space subspace W, and you want to find all vectors Ax such that Ax is equal to that component. Well, maybe I'm going to stop at this point because we only have a couple more classes, and and I think I'm going to spend the next two classes actually doing review problems for the final exam. So I don't really want to start anything new, especially today. But this linear algebra that we're using, especially the linear algebra of inner product spaces, has a huge number of applications in probability and statistics, numerical analysis, anywhere that mathematical analysis is used, psychology, economics. It's very, very, very useful. Anyway, maybe I'm just going to stop today right here. I will have the exams posted tomorrow, and I will be preparing a couple of review sheets for the final, which is pretty soon. So we have two more classes, one class on Wednesday and one class next Monday. And then the final exams a couple of days after that. Any questions before we?
No. Have a nice day, sir.
Do you have a question?
Oh, no, I was just saying have a nice day.
Oh, thank you very much. You too. All right, bye all.